In this section, 6.2, we're going to be computing areas between two curves. So previously, when we computed areas, we were just looking at a curve and the x-axis. But now we're going to be looking at two curves, and we're going to find the area between them. So unlike a normal integral that can be 0 or can be negative, when we look at the areas between two curves, it's always going to be 0 or some positive number. It will never be negative. So the idea is the same with Riemann sums. What we're going to do is we're going to make these rectangles, and we're going to add up the areas of these rectangles. And if we make these rectangles thin enough, then it'll nicely fill in between these two curves and we'll get an accurate area. So when we find the area, it's going to be an integral. But the key is that you want to always take the upper function minus the lower function. Super important is to graph your curves. It's very important that you see what these curves look like. And then maybe, if you're not sure, draw a representative rectangle so you can determine which function is the upper and which one is the lower. If limits of integration are not given, you may have to find the limits of integration based on your graph, which is why it's really important to have a graph. Okay? And like I said, whenever you integrate, you're going to do top minus bottom function. The reason why it's always top minus bottom, that's to ensure that this distance here is always positive. So in this box we have the definition of the area between two curves, and it's simply if f is greater than or equal to g, then you integrate f minus g, upper minus lower. So let's look at example 1. We have these two functions, f and g, and we want to graph these functions, see what they look like. Always very important to graph the functions. The first function f is going to be a line, and then our function g is going to be a parabola. So f, when x is -4, we have 0, and then it just goes up from there. When x is 0, y is 4. This is not really to scale. Our parabola g is opening up, but it's shifted down 2. So g is going to look like this. Again, this is just a sketch. I want this so that I can get a basic idea of the shape. So now we've graphed our functions. They're going to intersect at these 2 points. And it'd be really nice if I could figure out these points of intersection. So all I have to do is take my two functions, x plus 4, and set it equal to the x squared minus 2. So this turns out to be a quadratic equation. I'm going to go ahead and set it equal to 0, and then factor. So it turns into x squared minus x minus 6 equal to 0. So all I'm doing here is factoring so I can find these points where these two graphs intersect. This factors to x minus 3x plus 2. So I have x is equal to 3 and x is equal to -2. Going back to my graph, at -2 and at 3, that's where these two graphs will intersect. So let's go ahead, and now that we've already graphed it, we're going to find the area bounded by the curve. So when it says bounded, that means between. So it would be this area here that I'm shading in yellow. Oh, I always forget to do that. So when we look at b, we're going to set up our integral. And if we want to look at a representative slice, we would draw a representative slice and would see that our upper function, this green function, that would be f, and our lower function is going to be the red function, which is g, okay, because it's always upper minus lower. We're going to integrate with respect to x, so our x values are going to go from -2 to 3, and that's why it's important for us to see the graph and see where those points of intersection are. So our area is going to be the integral from -2 to 3 of our upper function, which is x plus 4, and we're going to subtract our lower function, which is x squared minus 2. And we're integrating with respect to x. If I get rid of the parentheses and combine like terms, I'm going to have -x squared plus x plus 6. And the integral is going to be -x to the third over 3 plus x squared over 2 plus 6x. And I'm evaluating from -2 to 3. This is going to be a negative. Putting in 3, it becomes 27 over 3 plus 9 over 2 plus 18. So it's upper minus the lower. If I put in -2 in place of x, I'm going to have negative would be a positive 8 over 3 plus 4 over 2 minus 12. Okay. So just doing those computations, I end up with 125 over 6. Now again, since we are finding the area between these two curves, we better get a positive number, or 0. If you had a negative number, that would mean that you would need to check your math and see how you set up your integral. Sometimes we're going to have to break up our graph into more than one integral when we're finding areas. In example 2, I have a function sine and a function cosine. So if I were to graph these functions on the interval from 0 to pi, let's look at this. So our sine function starts at 0, and then it goes up to 1, and then it comes back down at pi, and it's 0 again. Remember, I'm only graphing it on the interval from 0 to pi. But our cosine function starts at 1. At pi over 2, it's 0, and then at pi, it's 1. So it starts high, and then it goes low. So there's my graph, and it's just a sketch. I want to find the area between the curves on the interval from 0 to pi. Okay, so I'm starting at 0, and I'm going to pi, and I'm trying to find the area between these two curves. Okay? So I got to be careful because they intersect here at this point, which is pi over 4. So at pi over 4, what happens is my upper and my lower functions switch. So these are compound regions that I'm going to have to break up into two integrals because the upper and the lower functions switch. From 0 to pi over 4, I'm going to have cosine is the upper function and sine is the lower function. From pi over 4 to pi, sine is now the upper function and cosine is the lower function. Which means in part B, where I have to find the area between these two curves, I'm going to have to write two integrals. The integral from 0 to pi over 4 would be the upper function cosine minus the lower function, which is sine. So I'm going to add that area to the integral from pi over 4 to pi. Now my upper function is sine and my lower function is cosine. Okay, so again it's upper minus lower to ensure that your slice always has a positive. And if you need to look at the representative slices in the first region, I can see that the cosine is the higher, and in the second region, sine is the higher. Computing cosine minus sine is going to turn into sine plus cosine. So this would be the antiderivative of cosine is sine. This minus will turn into a plus because the antiderivative of sine is a negative cosine. So this turns into plus cosine. And I'm going to evaluate this from 0 to pi over 4. Then I'm going to add it to antiderivative of sine is negative cosine minus sine. And this would be pi over 4 to pi. If you'd like, you can factor out the negative in the second integral, but I'm going to leave it the way it is. So sine of pi over 4 is square root 2 over 2 plus cosine of pi over 4 is square root 2 over 2. And then I'm going to subtract sine of 0. Well, I'll just write 0. Plus cosine of 0 is 1. Okay, so this is my first integral. My second integral is negative cosine of pi. Cosine of pi is a negative 1. So this becomes a positive 1. And then sine of pi is 0. So 1 minus 0 minus negative cosine of pi over 4 is negative square root 2 over 2 minus sine of pi over 4 is square root 2 over 2. And then we'll just go ahead and clean this up. Here, this would become 2 square root 2 over 2, which is just the square root of 2, minus 1, plus, in the second bracket, that's going to turn into 1 plus the square root of 2. And again, I'm looking at exact answers whenever possible. It looks like the 1s are going to cancel, and I have 2 square root of 2 should be my solution. Again, this is an exact answer, which is preferable. Right, so that would be part A. What I'd like to do is go back up to the question. And the second part says, find the area bounded by the curves and the x-axis on the interval from 0 to pi over 2. So let me go ahead and sketch that again. We have this graph. But this time we're only going to go to pi over 2. So sine starts at 0 and at pi over 2 we're at 1. Cosine starts at 1, and at pi over 2 we're at 0. So we're supposed to find the area bounded by these curves and the x-axis. So what does that mean? So we're looking at the curves and the x-axis. We're looking at this region here. So you have to be real careful about how your regions are described so you can determine what area you're supposed to find. Unfortunately, the upper function changes. Okay? I start out with an upper function of sine. And then here, at pi over 4, it changes. And then cosine becomes the upper function. So think about this. I'm computing the area, and from 0 to pi over 4, it's just the sine curve in between the x-axis. So sine is the upper, the x-axis is the lower. And then from pi over 4 to pi over 2, it's just cosine. I'm going to be breaking this up into two integrals. The first integral goes from 0 to pi over 4, and the second integral goes from pi over 4 to pi over 2. So the integral from 0 to pi over 4 is just sine, plus the integral from pi over 4 to pi over 2 is cosine. And this becomes negative cosine, evaluated from 0 to pi over 4, plus cosine is sine, evaluated from pi over 4 to pi over 2. So again, just read real careful. Make sure you know what region you're looking at. So cosine of pi over 4 is square root 2 over 2, but it's a negative cosine. So it's going to be negative square root of 2 over 2 minus a negative cosine of 0, which would turn into a plus 1. So it's this piece, plus sine of pi over 2 is 1 plus sine, or minus, sorry, sine of pi over 4, which is square root 2 over 2. Okay, so it looks like this is going to be 2 minus square root of 2. And that is a positive number, so I probably did my math correctly. So what we've been doing is we've been looking at computing areas where we're integrating with respect to the variable x. But sometimes that's not the easiest way to go. Sometimes it's easier to integrate with respect to the variable y. And that would be in this particular diagram. Notice I don't have an upper and a lower function. What I do is I have a function to the right and a function to the left, or an outer and an inner function. So it doesn't make sense for me to integrate with respect to x. It makes sense for me to integrate with respect to y and take this outer minus inner function, or right minus left. So this is what a representative slice would look like. I would have the outer y value minus the inner y value, or the right y value minus the left. When we integrate with respect to y, it's the same as if we integrate with respect to x. It's always the right minus the left, or outer minus inner. Graph your curves. Draw a representative horizontal rectangle if you need to. Find your limits of integration if they're not given, except for your functions are usually written in terms of x. So you're going to need to solve x so you can have your function written in terms of y, because we're going to integrate with respect to y. So the integration is right minus left. In example 3, we want to find the area of the shaded region with respect to y. And the reason why we want to find this with respect to y is because hopefully you notice that we have a right function and we have a left function with respect to this shaded region here. Right, so we're just looking at this shaded region. Now, if I was going to integrate with respect to x, this would be kind of difficult. I'd have to break it up into pieces, but I'm going to go ahead and integrate with respect to y. When I integrate with respect to y, though, I have to rewrite my equations. So this parabola here that's opening to the right, this is the equation x equal to y squared. And this line is x equal to y plus 3. So this is already solved for x. And the limits of integration, if we're going to integrate with respect to y, on that shaded region, would be this y value here, which is -1, and this upper y value here, which is +1. Our integral is going to be from -1 to 1. The function on the right is y plus 3, right? Solve it for x, which it's already solved for x, and then you would put y in your integral. So it's going to be y plus 3, because that's the right function, minus y squared. We're going to integrate with respect to y, so it's a dy. And this becomes y squared over 2 plus 3y minus y to the third over 3. We're evaluating from -1 to 1, which gives us 1/2 plus 3 minus 1/3, so upper, minus the lower limit of integration is -1, so that becomes a positive 1/2 minus 3 plus 1/3. And after doing our math, we should get 16 over 3. All right, so let's look at one more example where we're going to integrate with respect to y. So let's say that f of x is -x and g of x is x cubed. We want to graph the functions and find the area between our curves from y is equal to 0 to y is equal to 2. So my limits of integration are given to me in terms of y, not x. Y is 0, y is 2. So that tells me I'm probably going to integrate with respect to y. But let's go ahead and look at the graph. Y, or well, actually I'll do the -x first. So -x is just a diagonal line. Right, so this is my f. And then maybe I'll use red for g. So that would be x to the third. And this would be my g. So I'm supposed to graph these functions and find the area between the two curves, f and g, and the y equal to 0 and y is equal to 2. Okay, well, y is equal to 0 is at the origin. Y equal to 2 would be this line here. What color do I'll do blue. So this is y equal to 2. So can you see the region between all of these? This would be the area that I'm trying to find. Now, if I was going to find this area with respect to x, I would have to set up two integrals because the upper and the lower functions change. If I was integrating with respect to x, my upper function is going to be y is equal to 2. My lower function is f until 0. And then after 0, it changes. The upper function is still y is equal to 2, but the lower function becomes our g function, which is the x cubed. So if I were to integrate with respect to x, I would have to break this up into two integrals and add them together to find the total area. So instead of integrating with respect to x, I'm going to integrate with respect to y. And I'm going to set up a slice, a representative horizontal slice, where I can see that my left function is g, my right function is f, and all I have to do is go from y equal to 0 to y equal to 2 and integrate with respect to y. So when I integrate with respect to y from 0 to 2, it's g minus f, and g is x to the third. Oh no, it's written as x to the third. Well, before I integrate, I'm going to have to change this g I'm going to replace with y and write it as y equal to x to the third. I have to solve it for x. So this is going to be the cube root of y equal to x. Or in other words, y to the 1/3 is equal to x. So y to the 1/3 equal to x would be my g. Now my f can be written as y equal to negative x. And I'm supposed to solve for x, so it's actually negative y equal to x. So that would be our f, negative y equal to x. Okay, now I'm going to go ahead and I'm going to set up my integral. My integral is going to go from 0 to 2. It's going to be y to the 1/3 minus a negative y, which would turn into a plus y, integrating with respect to y. All right, so now it's going to be y to the 1/3 plus 3/3, so y to the 4/3 over 4/3 plus y squared over 2. And I'm evaluating from 0 to 2. I'm going to clean this up a little bit. This becomes 3y to the 4/3 over 4 plus y squared over 2. All right. So this is 3 times 2 to the 4/3 over 4 plus 2 squared over 2, right? And then I would just be subtracting the 0 plus 0. This is not going to turn out to be anything nice. 2 to the 4th is 16, so we're taking the cube root of 16. and that's going to be times 3 divided by 4 plus, the other one's not bad, that's 4 over 2, so it's just 2. And I could clean up the cube root of 16. That's going to be 2 cube root of 2. So on the outside I would have a 6. Cube root of 2 over 4 plus 2. And then I can reduce the 6 over 4 to 3/2. So 3 times the cube root of 2 over 4 plus 2 would be an exact answer. But if you put this in your calculator, you'll get approximately 3.89, maybe, or something close to that. So that's it for this section. We're just finding the area between two curves, and you can either integrate with respect to x or with respect to y.